Hello, community partners. I am JuiceFS, the engineer mainly responsible for performance and the commercial version. This time, we have migrated the Python SDK from our commercial version to the community version. So today, I will introduce our Python SDK to everyone and provide some demonstrations, including some possible performance improvements, which I hope to discuss with everyone. First, let me introduce the background. On one hand, in many AI or data science fields, Python is widely used. So we provide a Python SDK to make it easier for everyone to use. Our product is fast. Additionally, in some environments, permissions might be insufficient, making it impossible to provide root access. Or in serverless environments, it might not be feasible to use our POSIX mounting. In scenarios where mounting in this way is not possible, being able to directly read and write data through the Python SDK would be much more convenient. Yes, this addresses a usability issue in certain scenarios. Another aspect is Fuse. If you are familiar with Fuse, you should know that under normal circumstances, the size of each request is limited to 1 to 28 kDLIB. Of course, we might be able to adjust this. Using DIO to allow it to reach a maximum of 1 megabyte can improve performance in some areas. First, this 128 kDB request limit can lead to what we call fragmentation of high performance, larger data requests, which then affects the overall read and write performance. This fragmentation also brings another issue if your requests are interdependent. In read mode, if you are doing cold reads, the relatively high latency can significantly impact overall performance. By using the Python SDK, we can bypass this 128 kB limit, thus avoiding this performance issue. Of course, as I mentioned earlier, we might be able to avoid this issue by using direct I/O, which can largely prevent this problem. First, let's talk about how to install it. Our current Python SDK has already been submitted to the Community Edition, and you can use this Python SDK by compiling from the source code. First of all, the Python SDK is based on the dynamic link library of the Java API or Java SDK we previously provided. We implemented an object for our JuiceFS client within this dynamic link library. Here, in the Python SDK, we have exposed some of the methods from it through Python. So, the entire installation process is not very complicated. One part is compiling this dynamic link library, and the other is packaging a Python package. Just install it, and that's it. Here, we will try it out. This is a repository for our JuiceFS, apart from the demo that we will show later. Most of the content here is from the main branch of our Community Edition. The content related to the Python SDK is all on the main branch, so we can directly demonstrate it here. First, we need to compile, because the compilation is done in the SDK directory. So we need to compile the dynamic link library this way. Okay, the dynamic link library compiles quite quickly. We first enter the Python SDK into the Python directory. In this directory, there is a just directory, which is the specific directory for our Python API, the Python SDK API. Inside here, we can see a setup and our source code in the CFS directory. So, once we are in this directory, we can compile the SDK. It requires a build package dependency. The build module is needed, and it also requires a virtual environment. Once compiled, it will appear here, and we can install it. Okay, now the Python SDK is like this, and it will be installed quickly. We have already formatted one here. File system, it looks like this. In a moment, we will go directly into Python to take a look at ours. How do we use this Python SDK, and what kind of API does it provide? Let's start by using help, because most of our documentation can be directly accessed through help. So there are no obstacles for everyone to use the Python SDK now. There isn't much content under the help of this package, but we can look at each object. Each of its classes is first provided in our most basic Python SDK. This is the FS client, and it has many usages or methods. We initialize a client, and its parameter list is right here, all key. Yes, it also provides some file system interfaces like open and rename, and of course it includes some extended interfaces like warmup and summary, as well as interfaces like RMLR. Yes, let's try initializing a client, which is the same as mounting. At the very least, we only need to provide a name and a meta address. Then let's list it first. Right. This is the content of the root directory of the file system we just created under the directory we just made. Let's open a file at random, and you should be able to see that the API for files here is almost completely consistent with the native file stream API in Python. Okay, let's take a look at what interfaces are available for operating on this file. These interfaces are fully compatible with the interfaces of the file object we get when we directly open a file in Python. Yes, so it's quite convenient for everyone to use in some situations. Environment, to directly use our Python SDK to open a file and integrate it into your existing logic. Yes, and we also need to demonstrate an extension. We just talked about the API of the client and the API of the file, and we can also support FSpec. The FA spec is a standard for a file system interface in the AI field or data science field. After we support this, voila, the most common thing you can use is something like Ray. Tools to create data interfaces for our support of FSpec. It is currently supported and has already been submitted to our community. Here, yes, through this method, we can use the interface of this spec. This is just a demo, and it's very convenient to use. The following parameters are what we need to pass to our CFS client, and the other usage methods are the same as our other FSpec abstract file systems. Okay, there are also extended APIs like summary info. If we have used these interfaces in the command line, everyone will have some understanding of them. We use them in the Python SDK. The result we return is a dictionary. This is the only point to note, which is for convenience. To make it easier for us to script using this interface, we use summary as an example. This way, when it returns as a dictionary, it is convenient for us to index. Okay. Finally, there's another example, a demonstration part. I'll briefly introduce it here. We chose an FFRecord data loader as a demo. Here, we want to verify something when we read through Fuse. At the beginning, it was mentioned that there is a 128K maximum request limit, but through the Python SDK, there is no such limit. Regarding FFWrapper, which was quite popular some time ago, it is an open source dataset format from Huanshang. It is a mode for random reading of large files, and it contains. Its file header contains something similar to metadata, which records the offset and length of each sample. This allows for precise knowledge of the location of each sample during random reading. In this situation, if we imagine reading through Fuse, then each time, for example in our case, if we read 3 megabytes, or each time it would be split into several 128K chunks. Here, the dependencies between these multiple 128K requests can lead to amplified delays. In the conventional reading mode, the delay will be amplified, leading to a deterioration in overall performance, which is a problem. Another issue is that if our 128K requests come one by one, our FS client will perform pre-reading. In the range of 1 megabyte to 4 megabytes, there will be an amplification issue of approximately 2 to 4 times. As long as pre-reading occurs, there will be read amplification, which will lead to some performance loss. So, we can explore whether implementing such a data loader through the Python SDK would be more advantageous. we have created a demo to attempt a comparison. This generated a dataset where each sample is approximately 3 megabytes plus or minus 500 kbytes SQPUT with a total of 1000 samples. Finally, it was through. Using the Python SDK to load, we achieved a throughput of 15 samples per second, whereas the official version using Record achieved 4 samples per second. Theoretically, this by 4 samples per second could be improved through direct I/O. However, in the official open version, direct I/O cannot be used by default. We need to modify it ourselves to make it work. If direct I/O is enabled, it can achieve 12 samples per second. You can see that this is quite close to what is achieved. Through the Python SDK, since this is a hacked version, we won't discuss those results here. Let's talk about the logic of this demo. Once this demo is organized, it will be included in the community version of the code. As an example, first, there's a file reader at the lower level. Where are you? I was just trying to find a document on the record format. Okay, it's not convenient here at the moment, and it's not included in the code comments. Mainly, several classes have been implemented one by one. It involves parsing the file format of the FFRecord and performing a correctness check. It is divided into 2 parts. One is reading the sample, and the other part is reading the file header, which is the initial header. When reading the header, if you need to perform a CRC310 check, this check is done when we initially load the dataset. During initialization mode, the contents of the file header are loaded, and according to the official format definition, record the offset of all the samples. Once recorded, it can serve subsequent reading operations. During the reading process, it becomes quite convenient and can directly support reader 1 and read batch. In this context, we have a logic where, in Python, it operates as a single-threaded processing. So, we cannot achieve concurrent read batch, which is a significant issue at present. This is a problem we encounter when using Python 4DK to load datasets. Therefore, we can see that when using RedBest, it is a very convenient process for parallel reading. However, here, we have to do it serially, but theoretically, we can offload it to our dynamic link library. We can also try to implement some asynchronous logic in Python. That would be relatively complex. Yes. So, the result just now was actually produced by a single worker, as noted here. Additionally, there are 2 other areas that are relatively confusing. Here, there is an open and a close, which actually support multi-threaded loading in the data loader, specifically the numWorkers parameter. The implementation logic of this parameter is that after the main thread is initialized and ready to start loading, it will fork several worker processes to handle data loading specifically, and then send the loaded data to the main process. Right, so we'll package the objects in the main process first and then pass them to the forked subprocess. In this process, our client definitely does not support this operation. Yes, so we also need to consider that if you use numWorkers for multi-threaded loading, we have to initialize a client in each process. Of course, the load is relatively small, and the additional burden it brings is not that significant. This is a low-level reader. The upper-level dataset is quite simple. It just calls this, and that's it. The data loader is the same. The data loader works just like our regular data loader. You just need to pass the dataset into it. Additionally, we have a script that directly uses the official library to generate a demo for FFR. We will try to run it here, and one of them will be executed at the lowest level by directly calling the current source code. This Python SDK initializes the Python SD client here, serving as a basic demo. This is the file reader, correct? This completes the passing of the FFRecord format with this data loader. Or this main, we use this main to generate the demo for FFR, and it can also perform loading here. Let's try it. Simply, I'm not sure if it's okay like this now, where, okay. So the directory of my current demo is not the same as the file I modified, right? So this demo will stop here for now. Later, there will be a direct comparison of the demo results. The script will also be placed in the community repository. This concludes the part about Python KK for today. Thank you all for watching.